Hi, my name is Mark Cantrell. I'm an applications engineer with the isolation group here at Analog Devices. Today we'd like to discuss EMI in the isoPower devices. If you look at our ADUM 5000, for instance, the power supply only part, we have an oscillator which generates 180 megahertz switching frequencies into a very tiny transformer. The signals are then rectified and regulated at the output. The issue is that these signals are extremely fast. The pulse period is only 5.6 nanoseconds, and the actual pulses themselves can be up to 900 milliamps at high voltages. This, when it's sent through the transformer and rectified, is turned into something that looks like a full wave rectified signal. This doubles the frequency to 360 megahertz. This gives us the two major frequencies of interest for our devices. 180 megahertz for the drive side, 360 megahertz for the rectification signal. Two main problems are, first, this 900 milliamps is too much for a standard bypass capacitor to supply in a timely manner, because the bypass capacitors have via inductance, their own internal inductance, and the power and ground plane inductances to overcome in order to supply this 900 milliamps of current. What this does is it generates a fairly large noise voltage on the power supply rails, which can conduct all over the system. If we look at our scope picture here, we actually can see a couple of hundred millivolts of power noise on a VDD line for one of our demo boards. Our other issue is that our part drives power from a primary side to the secondary side across a split in ground planes. From a DC point of view, this isn't a problem. Each side kind of works independently and hands power across fairly symmetrically, but at the frequencies that we're worried about, 180 megahertz and especially 360 megahertz, it generates differential voltages and currents across these ground planes, turning them into a fairly efficient dipole radiator. The best way that we've found to eliminate this kind of noise in the system is to short the dipole out. And the easiest way to do that is to give the image charge currents that are being pushed across this barrier a path back to the primary, which allows which basically shorts the dipole out and removes a lot of the emissions. In order to do this, it requires board layout modifications be made right at the beginning of the design process. In order to improve the conducted noise, in other words, the noise that's being conducted onto the VDD and power lines, we'd like to go through one circuit solution, PC board solution that helps immensely. Let's assume that these two things represent the input and the output power plane for a standard circuit board. We'll use this clear plastic as the circuit board material itself. Now, if we place the ground and power planes very close to each other, right on either side of a very thin layer, and these things can be, standard PC boards can be as thin as 4 mils, this creates a very effective low inductance capacitor on the input side and the output side. If you then place your circuit, your ADUM 5000 for example, with its bypass capacitors, if you make the ground plane be the top layer, you can have no inductance because there's no via, and then a very short via down to the power plane, and then once the noise is into the power plane, this becomes an extremely effective bypass capacitor, reducing the noise generated by the switching of the oscillator immensely, probably as much as an order of magnitude in most cases. Now let's address the problem of radiated emissions from signals being driven from a primary to a secondary across a gap. As I said earlier, the way that we found that shorts out that dipole is to add capacitance from the secondary to the primary. It has to be very low inductance, and it also has to be buried in a central layer of the circuit board in order to maintain the creepage and clearance of the entire board. Structures internal to the board can span isolation gaps, especially for basic insulation. There are no minimum distances required. So if we have a power plane and a power plane, and we build an isolated floating structure in that same plane, if we then lay the ground plane on top of that through a very thin layer of circuit board, as before, you see that we wind up with if we flip it over, you can see that we wind up with areas of overlap here and here, which creates, again, very good capacitors with an extremely low inductance path between them. This structure can easily bypass frequencies of 360 and higher megahertz. And again, placing the part very close to this structure allows the dipole to be shorted out and dramatically reduces the irradiated emissions. So let's look at a practical example of what we've just looked at in a mock-up of how to suppress radiated emissions from a PC board driven by a very high frequency oscillator. Here we have a demo board for the ADUM 5000. If we look at the screen, this is looking at the VDD line, so you can see the power supply noise. Here I have a near-field magnetic field probe, and if we look at it here, you can see the green is what's coming in off the probe, and here we have a Fourier transform of it. If we adjust the cursors to look at the maximum of the 360 megahertz peak, we can see that we're at 30 some odd dB of emissions. Now we can create that capacitive structure on this board very simply by taking a piece of copper tape, flipping the board over, and slapping it on the back. We've now created that same structure that we looked at earlier. And if we look at it again with the magnetic field probe, you can see that the emissions have dropped dramatically. It looks like a total of almost 15 dB down, just with a piece of copper tape on the backside of the board. The structure shown earlier is going to be much more effective because it's going to be well controlled, and the capacitance is going to be much higher for a smaller area because the 4 mil spacing on the board is going to improve that situation significantly. So if you want to have more information, more detailed information, please go to our website. We have an application note on this subject, AN0971. I strongly urge you to go and review that app note before you begin your board layouts, and you can avoid a lot of end of the project scurrying around to fix these kind of emissions problems.